Of now, you may recall that whenever we have talked about a definite integral, we have always wanted our function f to be bounded, real valued function on a closed and bounded interval ab. But one may ask, what happens if we want to deal with integrals where either the interval that we are considering is not bounded or the function is unbounded? So, more concretely, one may come across integrals of the form integral a to infinity fx dx or integral minus infinity to b fx dx, or in fact, more generally, minus infinity to infinity fx dx. One may also try to look at integrals which are of the form which are taken over closed and bounded intervals, all right, but where the function f is unbounded. The question is, can we deal with such kind of integrals? These questions lead us to the theory of improper integrals, which I am trying to introduce to you in the current video. First, we are going to tell you about a kind of integral, improper integrals, which are known as the improper integrals of the first kind. So here we basically consider integrals where the interval is unbounded. So whenever somebody tells you about improper integrals of first kind, you will always remember that we are talking about integrals where the interval is unbounded. So here we are going to talk about the integrals that we have just mentioned in my previous slides, where the upper limit is unbounded, lower limit is unbounded, and both the limits are minus infinity and infinity. So there are three types of integrals, improper integrals of first kind. First is where the integral is taken over the interval a to infinity, but the condition is f has to be integrable on each closed interval ax where x is bigger than or equal to a. Similarly, when we consider integrals of this kind, so here the constraint is f has to be integrable over this kind of integrals x comma b, where x is less than or equal to b. And similarly, when we consider integrals where the integral is taken over the interval minus infinity infinity, there the requirement is that f has to be integrable on every closed sub intervals of R. So that is given by AB, where A is less than or equal to B. So let us deal with these cases one by one. First, we are considering an interval which is unbounded above. So the upper limit is infinity. And of course, the constraint f is integrable on ax for all x bigger than or equal to a. So we say that this integral of ft dt taken over the unbounded interval a infinity is convergent. So the definition now that I'm going to give is quite intuitive. So we know that f is integrable on this kind of an interval. So let me write down this expression a to x ft dt. So we know that this integral exists because f is integrable on this closed interval, and it may be very intuitive that this thing is convergent if limit as extending to infinity uh, of this integral, this Riemann integral, exists. And if this integral exists, that means this is convergent. We simply define this integral, which is taken from a to infinity ft dt, to be equal to this limit that we have just written down, a to x ft dt. Let us look at a couple of examples which are reminiscent of the infinite series that we have two infinite series that we have come across. One is summation 1 by n and another is summation 1 by n square. So you may remember that this series diverges and this series converges. Let us check whether similar things take place over here. So let me try to compute these two integrals very quickly for you. So what do we do in order to compute this integral? We have to check whether the limit extending to infinity, so integral 1 to x 1 by t dt exists or not. But what is this limit? What is this integral? We know that this integral is given by ln x minus ln 1. So this is limit extending to infinity. So here we are going to make use of our fundamental theorem of calculus part 2. So this is going to be ln x minus ln 1, and we are going to take limit as extending to infinity. We know that ln 1 is equal to 0, and consequently we are only left with this part, limit as extending to infinity ln x, and we know that this is infinity, this is not finite. So this means that this integral that we have does not converge, or in short we may also write that this integral diverges. Let us look at this example now, where we are going to integrate this function 1 by t square. So how do we integrate this? So first we have to check whether the limit exists. So limit extending to infinity 1 to x 1 by t dt 1 by t square dt. So we have to first calculate this integral. So let us do it slowly. Limit extending to infinity, we know that minus 1 by t is an antiderivative of this function 1 by t square, and we make use of our fundamental theorem of calculus part 2 to compute this integral. So in particular what will happen is that we are going to put minus 1 by x minus minus 1. So we are left with this quantity, limit extending to infinity 1 minus 1 by x, and as we can see that x goes to infinity, 1 by x goes to 0, and as a consequence this limit is equal to 1. So this limit, what we have seen, converges. So the improper integral converges. Let us go to the second type of the integral of first kind, improper integral of first kind, that we have just introduced. So here we are going to look at the integral where the lower limit is minus infinity, and of course our constraint was that f has to be integrable on every closed interval of the form x comma b where x is less than or equal to b. So we say that this integral is convergent, or sometimes we say that this integral converges simply if. So we cook up the definition as we have done in the first case. So what do? We write down the integral xb of ft dt. We know that this integral exists, and then we simply take limit as extends to minus infinity. So if this limit exists, then we say that this improper integral taken over minus infinity to b of ft dt is convergent. And if it is convergent, as before, we simply define this integral to be equal to the limit that I have just written down above. So integral from x to b ft dt, and limit x tends to minus infinity. Let me work out another example which corresponds to this kind of an integral. So here I have taken the function t to the power t. So you know that if I want to compute the integral, I have to make use of integration by parts. So just to make sure that you have not forgotten about it when you are looking at this video, I have given the statement over here. So for this, again, what do we need to do? First we need to compute this integral x to 0, and of course here x is less than 0, and I'll take the limit later. So you could also do it this way: first compute the integral and take the limit later. So 0 to x, so x to 0, t e to the power t dt. So 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 let me try to define what is our ft and gt here. So we can simply take ft equal to t and gt is equal to e to the power t. So for integration by parts, we need two functions, f and g, where f has to be differentiable and f prime has to be integrable. So let us see if satisfies these two conditions. Clearly f is differentiable because f prime t is equal to 1, and f prime, which is again 1, is integrable clearly. So what happens with gt? G needs to be integrable and it must have an antiderivative in this interval x comma 0. But you can easily check that this is true, and e to the power t itself acts as an antiderivative for this kind of function for this g. Okay, so now we are in a good situation to apply our integration by parts. So we see that this is equal to f of 0 g of 0 minus f of x g of x minus integral from x to 0 f prime x. So here f prime t is nothing but equal to 1, and gt, big gt, is simply e to the power t dt. So what is f of 0? We see that f of 0 is equal to 0, so this term is gone. So what we are left with here is the following: we have minus x e to the power x, and here we simply apply the second part of the fundamental theorem of calculus to see that we are going to get e to the power t, and the limit is taken from x to 0. So the final answer is the following: minus x e to the power x. So then you have minus 1, and then you have plus e to the then you have plus e to the power x. And as you can see that if we take the limit, so what is then the limit x tending to minus infinity? So x tending to minus infinity of this quantity, integral integral x to 0 t e to the power t dt, is equal to limit x tending to minus infinity minus x e to the power x plus e to the power x minus 1. And you can see that this goes to 0 as x goes to minus infinity, this goes to 0 as x goes to minus infinity, and we are only left with the quantity minus 1. So in principle, what we have obtained shows that the integral that we have started with here, integral minus infinity to 0 t to the power t, converges. So this integral is convergent. Okay, so now we are in the last case already. So what was the last case? We were given an integral of ft dt taken from minus infinity to infinity. Our constraint was f has to be integrable on every subinterval, closed and bounded subinterval of R. And we say in this case that f is convergent if both this both this integral and this integral exists. So what is this integral? So we have already seen how do we make sense of this integral. So the existence of this integral, the integral written above, depends on whether limit extends to infinity 0 to x ft dt exists or not, and similarly here it depends on the condition whether limit extending to minus infinity x to 0 ft dt exists or not. So if it so happens that it is convergent, that means both these improper integrals exist. Then we simply define the uh, integral minus infinity to infinity ft dt as the sum of these two integrals that we have talked about. So now we say, now we consider this limit first. So suppose we consider this limit. So first of all, by our constraint, we know that given any real number x, this integral is always well defined because this function is integrable on the interval minus x comma x. So if it so happens that as we take limit as x tends to infinity of this integral minus x to x ft dt exists, then it is called the Cauchy principal value of the improper integral minus infinity to infinity ft dt. So if this integral that we are talking about is convergent, and then we can make use of our domain additivity of Riemann integrals to see that integral from minus x to x ft dt is equal to integral of ft dt taken from minus x to 0 plus integral of ft dt taken from 0 to x. And this equality implies that if this integral, this improper integral which was taken from minus infinity to infinity is convergent, then then we know that these two things have to be convergent, and as a consequence this has to be convergent as limit x goes to infinity. So the convergence of this improper integral guarantees the existence of Cauchy principal value. However, it turns out that the converse is not true. So I leave this as an exercise. Leave this as an exercise to you. So you may try the function if t equal to sine of t to understand what is going on over here. So let me finish with a very quick example. So here we are trying to consider the integral from minus infinity to infinity 1 by 1 plus t square dt, and we want to check whether this is convergent or not, and if it is convergent, what is the value, and if it is not convergent, then the question does not arise at the first place. So let me try to work it out. So what we are going to do, we are going to take this integral from 0 to x and dt. So let me not be fancy and write it in a rather proper way. So this is going to be tan inverse x minus tan inverse 0 by, after using the second fundamental theorem of calculus, or the fundamental theorem of calculus part 2. And if we want to apply the limit as x tends to infinity on this integral 0 to x 1 by 1 plus t square dt, we foresee that this is equal to 0, and this is going to be simply pi by 2. So okay, the first limit exists. So what about the second limit? So you can also check very easily that limit extending to minus infinity integral x to 0 1 by 1 plus t square dt is also equal to pi by 2. So what we have just shown is that this integral that we started with is convergent, and not only that, the integral is equal to the sum of these two parts. So the sum of these two parts, so pi by 2 plus pi by 2, which is equal to pi. So I will finish this video with a very interesting and well-known example. So it will not take much time from here. So what is the example? Here we are going to consider this integral which is taken from 1 to infinity of the function 1 by t to the power p, and we ask when is this integral convergent. Okay, so this is of course an integral of first kind, and in fact of the very first type that we have just mentioned. So here we have only the upper limit has infinity. So first, what happens if we take p equal to 1? So then this integral comes to this integral from 1 to infinity 1 by t dt, and we have seen that this integral diverges in just our previous slide. So this leads us to the case when p is not equal to 1. So let me try to compute this case. So when compute this integral from 1 to a 1 by t to the power p dt, and if you do all the calculation correctly, you will end up in this position: 1 by 1 minus p 1 by a to the power p minus 1 minus 1. And if I want to take limit as a tends to infinity, I have done the full calculation here. It turns out that if p is bigger than 1, then this limit is equal to 1 by p minus 1, and if p is less than 1, then this limit is infinity. So what we have just shown is the fact that this integral, what we were interested in, converges only if p is bigger than 1, and it diverges if p is less than 1, and also in the case when p is equal to 1. We will come back to improper integrals of the second kind in our next video.